Plan seminar. Today, we're welcoming Martin Grohe to our group. He's a professor at RWTH Aachen University, where he holds a chair for the Logic and Theory of Discrete Systems group. And his research focuses on logic, parameterized complexity, finite model theory, database theory, and descriptive complexity theory. And today he will present us his paper on the descriptive complexity of graph neural networks, which is analyzing the power of graph neural networks in terms of Boolean circuit complexity and descriptive complexity. I'm super excited to have you here today, Martin, and you can take it from here.
Okay, thanks for the invitation. So, yes, I'll speak about descriptive complexity of graph neural networks, relations to logic. I'm interested in this stuff for various reasons. One is certainly that this connection between logical reasoning and neural reasoning, if you will, interests me. And for graph neural networks, you have some very tight and interesting connections. Now, I'm not sure I've pitched the talk right. So it may be that most of the talk is stuff that you know. I mean, I put the new stuff on where I really go into descriptive complexity towards the end. But on the other hand, I think what I present here is how this evolved. So it makes some sense to me at least. So let's just get started. Oh. Okay, this way works. So graph neural networks, I'm not sure if everyone is familiar with graph neural networks. Let me quickly go over them, also to introduce my notation and terminology. So graph neural networks are deep learning architectures for machine learning problems on graphs. You can view them as a generalization of convolutional neural networks from the rigid grid structure that you typically have there to more flexibly structured data. They have a wide range of applications, and I'm also working on some. For example, I'm working with people in chemical engineering, in electrical engineering, most recently on power grids, also in physics. So this is quite interesting, but this is not what I'm going to talk about today. Today, we will talk about the theory, and we focus on kind of the core GNN architecture, and they are sometimes called message passing graph neural networks, or also aggregate combined graph neural networks. So the basic principle is this: a graph neural network is basically learned distributed algorithms operating on the nodes of a graph. So you have a graph here, and at any point during the computation, every node of the graph has a state, which is just some vector. Okay, and they have some initial state. So let's just, in this example, assume the initial state is the all ones vector. And then based on their current state, the nodes send messages to their neighbors. Okay, and they receive messages from the neighbors, and actually they send messages all around, and basically every node sends the same message to all neighbors, right? Okay, and then they receive the messages from the neighbors, aggregate them in some way, and update the state. So now we have a new state. Based on this new state, we send new messages, we update the state, and so on. And basically, well, in the basic model, we do this for finitely many rounds. Basically, the functions that we apply in each of these rounds or in each of these layers are different functions. So zeta t is basically the state vector I have after t steps. And I'm going to explain how this is computed. That's basically what the algorithm does. So we have some initialization. So zeta 0 at every node may encode node labels, may also have additional features, for example, random features. And we'll see later that they are very important. Then in each round, basically, we aggregate at every node the states of all neighbors. Okay, so here we have the current state after t-1 steps. And this is a multiset, so a set where elements may appear more than once. And this goes over all neighbors. So we look at all the states, at the multi-states, now aggregate this. For example, we just sum up the vectors. And that we call alpha, okay? In general, this aggregation function should be a symmetric function so that we can apply it to a multi-set. Sum, mean, and max are the ones typically applied in practice, okay? And we can also apply them to a message function that is first transforming the state into something else, but that doesn't really make a difference for the theory. Okay, so let's just imagine aggregation is summation. That's the easiest to think of, I believe. So we add up all these vectors and then combine this aggregated value with the old state of the node to compute the new state. Okay, and these the aggregation function I've described, the combination function here is just a function in the simplest model computed by a feed-forward neural network. You can do something more fancy there, but let's say we just do that, and the parameters, of course, are learned. Okay, then sometimes we look at a variation of this where we add global readout, or this is also called adding a virtual node. And then we take another aggregation, and that's over all states of all nodes, not only the neighbors, but all. That will be the same at every node, and we call it gamma. Okay, and then in the combination, we not only take the old state, zeta t minus 1, the aggregated value of the neighbors, but also this global aggregation, and put this in. So both variations can be useful, and basically most of our results have variants for these two. I won't talk much about this, but occasionally this is important. Okay, so that's the basic model. And then we iterate this for a couple of rounds. Let's say here we have this simple update rule. And now we can say this computes a function. How do we get the function? Well, actually, we can compute functions defined on the nodes of a graph, node level functions. And they map every graph to a function from its vertices to some real vectors. And the way we do this basically is we iterate for the D levels, the D layers of our graph neural network. And then we apply some learned readout function, again computed by a feed-forward neural networks. Okay, we simplify the notation a little bit. Okay, and then we can also compute graph level functions, which are defined on full graphs. And what we do for this is basically we aggregate the states at all nodes we get in the last level. Say again, we add them up and then apply some feed-forward neural networks after that. Okay? This way we can compute functions, and of course we can learn the parameters of all these individual things, the combination, the readout here, this aggregated readout here. Okay, and if we apply message function here in addition, we can also learn their parameters. So that's the basic model. So it's a very simple distributed algorithm that we apply. We send message to the neighbors, receive matched messages from the neighbors, and then update states. All right. Now, one important thing to note is, and that's also a reason why graph neural networks have become so popular, typically we want functions that we compute on graphs to be invariant in the sense that they do not depend on the actual representation of the graph, but just on the isomorphism type. Isomorphic graphs should get the same function value. Okay, and the same for nodes. That's a bit more complicated to formulate. It's typically referred to as equivariance. Basically, if we have isomorphic graphs and an isomorphism between them, then the function value should be the same at a node and its image under the isomorphism. Okay, so that's automatically satisfied by the functions computed by graph neural networks, but it wouldn't be satisfied, for example, if you fed just the adjacency matrix of a graph into a feed-forward neural network, because a graph has many adjacency matrices depending on in which order you list or map the vertices to rows and columns. Okay, so it's nice that we have this, and yeah, in graph neural networks we have it automatically. Then another interesting variant of the model is to apply graph neural networks in a recurrent computation. So basically what we've said so far is we have D layers, and in round one, we apply the functions of the first layer, then the second, the third, and so on. But we could also say we just have one layer and apply it over and over again. And that's what a recurrent GNN would do. So we take a single layer, apply it repeatedly. We only have one combination function, one aggregation function, and yeah, we apply it over and over again. For how long? Well, we can determine that at runtime, maybe depending on the size of the input graph, or depending on the sequence of states we observe. For example, if we see them converge, then we might stop, okay? But we do not require any kind of conversion. We can just say at runtime we stop after n steps, where n is the number of vertices of the input graph, whatever we want. I won't talk about these recurrent GNNs very much in this talk, but I think it's a very interesting model. And it's a model where I really don't understand the complexity and the connections to logic. So for these bounded depth, fixed layer networks, well, the results I'm going to present give a very clear picture. If you look at the recurrent model, basically we have no idea what happens. So there are interesting open questions. Okay. So before I continue, I want to digress a little bit. And I then want to talk about one very basic result that is underlying much of the theory, and that is a close connection between graph neural networks and an algorithm known as the Weisfeiler-Lehmann or color refinement algorithm. So let me digress and talk a little bit about the algorithm. It's, in its simplest form, a very simple combinatorial algorithm that was initially proposed as a graph isomorphism heuristics. And what it does, basically, it iteratively computes a coloring of the vertices of a graph. And the goal should be that if two vertices are structurally different or formally belong to different orbits of the isomorphism group, we want them to get different colors. Now, the algorithm does not achieve this, but that's kind of the goal. And the way we do this is very simple. Initially, all vertices get the same color. And then we repeatedly do the following. We repeatedly do refinement steps in which two nodes get different colors. If there's some color, the current coloring, such that the two nodes V and W have a different number of neighbors of that color. Okay? And then after a while, well, basically we're interested in the partition into color classes we get. And after a while, this will stabilize. We have n vertices, so after we always refine a partition, we always add colors. And after at most n steps, no refinement will be possible. The coloring stays stable, we say, and that's what we want. Okay, so let me just show you this algorithm. I think I have to share the other. Okay. Okay, now you should see my color refinement demo by, actually Holger Dell wrote this. And so this is our initial graph. All vertices have the same color, blue. Okay, now in the first round, two vertices should get different colors if they have a different number of blue neighbors. There's only one color blue. So for example, this one has 3 neighbors. This one here has only 2, so they should get different colors. Okay, yeah, that happens. This one is red. This is some funny green. Okay, and this one has 4 neighbors, it's purple. Okay, now let's see. Let's look at these 2 green, this one and this one. Do you see what I'm doing? That I'm moving the vertices. Okay, so this one here has a pink neighbor, a purple neighbor. This one has this red pink neighbor. So now, even though they both have 2 neighbors, they should get different colors. And indeed they do. And now we can look again at 2 vertices of the same color, say this one here and this one here. This one has a reddish neighbor. This one is more pink, so they should get different colors. And I think they have different colors, although they are hard to distinguish, so I better stop.
Yeah, they have different shades in orange, if you look closely.
Shades in orange, but close. Actually, here on the side, you can also see the different colors. But anyway, so
motifs, right?
yeah, basically, I mean, you can describe all the colors by trees, which always tell us how many neighbors do we have on each level, and that's what you see here. Of course, you probably can't see very much, in particular if you're looking at your mobile phone right now, then it's going to be difficult. But anyway, it's a simple algorithm. I see you think you see the point. After 5 steps here on this graph, it stabilizes.
Is this online? Can we play around with this?
This is online on GitHub somewhere. Yeah, I can send you the link.
Okay, thank you.
It's very pretty. You can also copy the link. This is just a local installation of this if you want, but it's on GitHub somewhere. You can also search, I suppose, Holger Dell color refinement. Let me go back to my talk. Okay, so we're back at the slides. Everyone with me? Okay, this is color refinement. Now, color refinement is essentially the same as the one-dimensional Weisweiler-Lehmann algorithm. We'll also talk about higher dimensional Weisweiler-Lehmann algorithms in a minute. There's a small difference that is often ignored, but is relevant in this context. Basically, one-dimensional Weisweiler-Lehmann would also count non-neighbors of each color. And that may make a difference, for example, if the graphs have different sizes. So color refinement is actually the one that is closest to graph neural networks, but usually this is ignored and people just talk about Weisweiler-Lehmann when they mean color refinement, or maybe one-dimensional Weisweiler-Lehmann, which would be related then to the graph neural networks if we add global readout. But let's not get into these details here. Now, the algorithm is extremely efficient. That's, for example, why it's used as a subroutine in almost all modern graph isomorphism tools. It runs in almost linear time, no large hidden constants. So it runs really well. Of course, there's this log factor, which makes it a bit worse than linear. We were wondering a while ago if we can get rid of it. It seems we can't. We cannot prove this absolutely, but for a fairly large class of algorithmic strategies that includes all attempts people have made to compute this stable color. So this is why it's a really useful algorithm. It has other applications, but we want to relate it to graph neural networks. Before I do that, let me just explain how it's used as an isomorphism test. Basically, we would say that color refinement distinguishes two graphs if their color histograms differ. That means there's some color where we have different numbers of vertices in the two graphs. So we just look how many red, blue, green vertices are there and compare this. If it's different, the graphs cannot be isomorphic. If it's the same, they can still be still be non-isomorphic. Our coloring is just not good enough. That may happen. So it's an incomplete isomorphism test, but since it's so efficient, it's always a good idea to use it as a first test and then maybe as a subroutine after other steps, for example, in a search tree. And actually it works on almost all graphs in a precise probabilistic sense. I don't want to go into it, but it also may easily fail. For example, if you look at these two graphs, cycle of length 6 versus 2 triangles, well, initially all vertices have 2 blue neighbors and it stays like this. So the coloring is never refined, but clearly the two graphs are non-isomorphic, even though they both have 6 blue vertices. Okay, so that's how it is. And that's also something to keep in mind for graph neural networks, because when we characterize them by color refinement, we also know that they can't do distinguished graphs. Color refinement cannot distinguish. Okay, so the algorithm is really nice because it has surprising connections to all kinds of different things. Among them graph neural networks, but also other things. For example, we have a logical characterization. So the theorem says if we have graph GNH, we want to know what it means if color refinement does not distinguish them. Well, one thing it means is they satisfy the same sentences of a logic called C2. That's a 2-variable fragment of first-order logic with counting quantifiers saying there exist at least n elements x satisfying something. Now this n here is a constant. It's not a variable. That will be important later. Okay. So they are equivalent in this logic, and that's a logic that has received a lot of attention in descriptive complexity and finite model theory. Then the next is an algebraic characterization. Basically, the graphs are fractionally isomorphic. That means there is a doubly stochastic matrix satisfying this equality. Now, if we would replace doubly stochastic by permutation matrix, this would mean the two graphs are isomorphic. So it's a relaxation, if you will, an LP relaxation of a natural integer linear program for graph isomorphism. And the last one is that if we count homomorphisms from trees into our graphs, then the numbers we get are the same for both graphs. So the nice thing about this is that all these characterizations are not obviously the same in any way, but still it all fits and they are all equivalent. Okay, let's move on quickly. One slide about higher dimensional Weisweiler-Lehmann. So in the k-dimensional version, instead of coloring vertices, we color k-tuples of nodes. Okay, this goes back to a paper of Weisweiler and Lehmann, where they looked at this for k equals 2. It's called the classical Weisweiler-Lehmann algorithm. And then it was later generalized by Babai around 1980. And this also plays an important role in the theory of the graph isomorphism problem. Running time is much worse. So basically, this algorithm does not scale very well. So in practice, it doesn't play a big role. In theory, it does. The one-dimensional version is essentially the same as color refinement. I already told you there's a small difference. The k-dimensional version is much more powerful. It's actually very difficult to find graphs that are not distinguished, say, by the three-dimensional version. But actually, if such graph exists for every k, even if you go with k up to something linear in the size of the graphs. So that's a well-known result by Seifer and Immerman. Really nice construction. And for all these characterization of color refinement we had in terms of logic, systems of linear inequalities, homomorphism counts, they can all be generalized to the k-dimensional version, which is also nice and also shows that this is very robust. So now let's get back to the graph neural networks. So these were our graph neural networks. Just to remind you, we have this initialization state where we encode the node labels in some vector. Then we go for D rounds, and in every round we first aggregate the states of the neighbors. Then we combine them with the old states of every node, and we have the new states. Yeah, and we do this for D levels, and then we apply a readout function either to every node. Okay, and here I put an index n to refer to the graph neural network I'm talking about. Or we compute a graph level function, where we first aggregate all the states and then apply some readout function to it. Okay, so that was graph neural networks, and the result, which is actually not too hard to prove and was proved independently in these two papers by Morris and my student Martin Ritzert and a couple of other people, and also by Xu et al. And it says that for all graphs, the graphs are distinguishable by a graph neural network if and only if they are distinguishable by color refinement. So we add one more equivalence to this list we had before, where we have all the different characterizations of color refinement. Okay, and why is it? I think it's relatively easy to see that, or yeah, at least I found when I looked at graph neural networks, they immediately reminded me of the Weisweiler-Lehmann algorithm. I was working on graph isomorphism, so I know that stuff. Basically, aggregating the states of the neighbors, information that we have already gathered as the neighbors, is precisely what Weisweiler-Lehmann or color refinement does. Basically, the colors encode the states, and they collect all information that we can possibly get by sending messages to the neighbors and aggregating that. Okay, so it's quite clear that graph neural network cannot distinguish graphs that cannot be distinguished by color refinement. The other direction, well, we have to construct graph neural networks that essentially compute the colors by the color refinement algorithm, and there's two ways of doing this. Xu et al. Basically applied the universality of feed-forward graph neural networks to construct a function that basically does the same thing as color refinement. One has to say that this leads to graph neural networks of size exponential in the graphs we want to distinguish, but it can also be done with polynomial size if you do the construction by hands. That's what we did in our paper. Okay, so in terms of distinguishing graphs, graph neural networks do exactly the same thing as color refinement or Weisweiler-Lehmann. But we're usually not so much interested in distinguishing graphs, but we're interested in computing functions on graphs. So let's look at that. And there's a first very nice result by Barcelo and al. And they say, okay, let's say we have a property of graphs that is expressible in this two-variable counting logic. that we've already seen before. Then this property can be decided by a graph neural network. Okay, so there's also a variant of theorem for properties of nodes of the graphs. I don't want to get into this now. They also prove the converse of the theorem. If this property is definable or expressible in first order logic, then actually there's an equivalence between graph neural network deciding the property and expressing the property in the logic. But there are properties not expressible in first order logic that can be computed by graph neural networks, but are not expressible in this logic C2. Okay, so the equivalence does not hold in general. Okay, what is nice about this result, also compared to the previous result, basically the distinguishing result says, if you have two graphs, you can construct a graph neural network that distinguishes them. And this graph neural network will depend on the two graphs you start from, or at least it will depend on their size. There's no way around this. So basically, for every size, we have a separate graph neural network. Here we have a uniform result. We have one graph neural network that expresses the property across all input graph sizes. That's something to keep in mind. Okay, there's also one restriction that the proof assumes that we have an activation function like ReLU or a linearized sigmoid to be able to compute Boolean functions exactly and not only approximately. We do not know if the theorem also holds if we assume GNNs with, say, logistic function as activations or hyperbolic tangent. I think that's an interesting question. I couldn't prove it for these. So basically, the approximation error there will kill us when we try to get a uniform result. Okay, now, what we also did in this paper with Christopher Morris is propose a higher order version of GNNs where we pass messages between tuples of vertices. And then we show that this corresponds in terms of distinguishing graphs to the k-dimensional Weisweiler-Lehmann. Okay, so as a corollary, in some sense, you can say that order k GNNs have the same expressiveness as the logic, well, the fragment of this counting logic with k+1 variants. Okay, now something very interesting is the question, what happens if we initialize the states of the nodes randomly? Okay, and that's something we typically do in practice because it really helps. Okay, so maybe you have some fixed labels which correspond to whatever information you want to encode. And then you also add some random features, say normally distributed with mean 0, variance 1. Okay. Now, typically for such GNNs with global readout and with random initialization, we always assume a global readout on each layer. As I explained in the beginning, that's convenient here. So let's just do this. Now, such a GNN with random initialization computes a random variable and not a deterministic function. But this random variable is still invariant or equivariant. So we don't lose this. If we would assign arbitrary initial values, say just number the vertices, then we would lose our invariance. Here we keep the invariance, but of course the outcome depends on the random initialization. So we compute a random variable. Okay, but then, for example, if we want to compute a Boolean function, we can repeat this a couple of times and then take a majority vote or something like this. So we can use it just like a random algorithm. So there's no real problem there, but That's always an issue when people talk about this. So I just wanted to mention this. So the random variable is still invariant or equivariant. Okay. Now it can be shown that GNNs with random initialization are substantially more expressive than GNNs with constant initialization. So this can be experimentally demonstrated. Actually, many interesting combinatorial problems can be expressed by GNNs with random node initialization. And basically, we proved some kind of universality results. It's actually a simple result, which reads as follows. So let's say we fix two error parameters, epsilon and delta, and we fix an n, which is the size of the graphs we look at. So this is a non-uniform result. We have some function defined on the class of all graphs of order n, maps them to 0, 1, or any interval of bounded length. Then there is a graph neural network, n, that approximates this function f in the following sense. So for all graphs, the probability that the difference between f and the function computed by the graph neural network is at most epsilon is more than 1 minus delta. Okay. Now, this is non-uniform. This neural network depends on n, and actually it depends exponentially on n. I think, to me, non-uniformity is not even the issue, but the fact that it's exponential in n, that's the real issue, the real problem with this result. So basically, it's the GNN is just some glorified version of table lookup here in this result. Okay, we also have a node level version of this. Yeah, and these things are set. So now let's move on to the descriptive complexity part, finally. So what's our goal here? And that's, from what I understood, what Lena says, that's something many of you are interested in. We want to somehow understand how the power of neural networks relates to the power of classical Boolean computation model, and compare it to complexity theory, to logic, and so on. So the type of Boolean models we're interested in here are circuits with threshold gates. So that's just Boolean circuits which have threshold gates, and these T threshold gate evaluates to 1 if at least T of its inputs are 1. So here's an example of a threshold circuit that basically evaluates to 1 if an even number of input bits is 1. And basically, for every number of input bits, you have such a circuit of this depth 3, right? So bounded depth circuits. It's known that without threshold gates, you can't do this. TC0 is the class of all languages decidable by a polynomial size bounded depth family of threshold functions, or you can say the class of all Boolean functions. Okay, and that's the class we're interested in. And for me, the starting point to this is work by Wolfgang Maas from the 1990s. This is actually a really nice paper where this result is from. And he says, okay, let's look at a family of Boolean functions or a language. Then the following are equivalent. This family is in TC0, if and only if it is computable by a bounded depth polynomial size family of feed-forward neural networks with piecewise polynomial activation functions. What makes this interesting is that the weights of these neural networks can be arbitrary real numbers. So the essential step in the proof is that the arbitrary real weights can be replaced by rationals and rationals that are not too long. Okay. And I always liked this paper, and I thought it should be possible to to lift this to graph neural networks. It is. Unfortunately, the proof techniques do not lift at all. And the reason it's not so easy to lift this is that here the input to the feed-forward neural networks that we observe is basically a fixed to 0, 1 vectors. And we could generalize this to inputs from a bounded interval. But it doesn't go for arbitrary real functions. Then the proof just doesn't work. However, if we look at graph neural networks, we may have graphs of arbitrary input size, and then the aggregation function will compute very large values, which are unbounded. So we cannot easily lift this because we have to deal with neural networks processing unbounded values. And math techniques do not give us this. However, we basically can still prove something like this. Now, I also want to make the connection to logic. That's even a bit tighter towards the GNNs. So we look at another first order counting logic, FOC. And the difference to this logic C I looked at before is here we also have variables ranging over numbers. And we have arithmetic on these variables. So now we can say there exist more than n elements, and n is also a variable. That makes the logic more powerful. Okay, so the difference between this logic we looked at before and this FO plus C is that both allow counting, but in C we only have numerical constants. Here we have numerical variables. Okay, and there's a nice result going back to Barrington, Immermann, and Straubing. It's not from 1990, it's more 1998 or something. I got this wrong. Anyway, it has two versions. The uniform version is a language is in D-log time uniform TC0 if and only if it is definable in this logic FO plus C. And the non-uniform version says the language is in non-uniform TC0, which is the default, if and only if it is definable in this logic FO plus C, but now with, sorry, this is a bit messy, with built-in relations. And that means we have additional relations the logic can access, and these relations depend not on the input graph, but on the size of the input graph. That's how we can introduce non-uniformity into the logics. Okay, and now here are the results relating this to GNNs. The first is just an upper bound for the expressivity. And remember, we had this lower bound from Barcelo et al. They said everything that is expressible in the logic C2 is expressible by a GNN. Here we say, okay, now assume we have a function that is computable by a GNN with rational weights and piecewise linear activations, then it is expressible in this logic FO2 plus C, the two variable fragment of this stronger logic. So if G there is the class of all graphs. If we combine this with the Barcelo result, we basically sandwich GNN's expressiveness between these two logics. Here both inclusions are strict. Okay? But we want an exact characterization. So let's move on. And a crucial step will be to look at families of GNNs. And we can also get away here. We have rational weights, piecewise linear activations. We want to get rid of it. We look at a family of activation functions that we call rational piecewise linear approximable. That's an artificial definition that I chose because it includes all common activation functions, like logistic or whatever you want, whatever is used basically falls into this class. Okay, and then we have the following, and this is an equivalence now. if we have a function defined on a Boolean function defined on the class of all graphs, it's computable by a polynomial size, bounded depth family of GNNs. They may use arbitrary real weights and RPL approximable activations. So all the typical activations that we may find. Then the second can be seen as a normal form. The same function is also computable by polynomial size, bounded depth family of GNNs with rational weights and just using ReLU as activations and only using summation as aggregation. Okay. And the third is F is expressible in this two-variable fragment of the counting logic. But now here we have this non-uniformity. We look at families, non-uniform families of graph neural networks. So we need built-in relations. Okay. So that's the characterization, a logical characterization of the power of graph neural networks. If we add random initialization, it gets even nicer. We basically say, okay, again, we have a Boolean function on graphs. It's computable by polynomial size bounded depth family of GNNs with random node initialization. We can add arbitrary real weights and again, these RPL approximable activations. Then we have the normal form, same thing, but now with rational weights, ReLU activation, sum aggregation. Interestingly, for the logical characterization, we get rid of the randomness. We say F is expressible in the order invariant fragment of the logic. Now, I just wanted to mention this. I'm not going to explain this, but the fourth point is maybe the main result. It's in TC0, non-uniform TC0. So if we add random node initialization, we're in TC0. Or we have precisely TC0. We have been in TC0 before, but now we can express everything in TC0. And the reason we can do this is, well, maybe the first puzzling thing is that here we have a randomized model. Here we don't have any randomization. But basically what we can always do, that's known as the Edelman trick in complexity theory, we can trade a randomness for non-uniformity. So here we have non-uniformity and we can use it to simulate the randomness. Now for the other direction, it's more difficult to explain what's happening there, but basically to simulate TC0 in this logic, which corresponded to graph neural networks by the previous theorem, we need a linear order on the input graphs. But it doesn't matter which one. We get something that is order invariant. Now, the random initialization, the random weights on the nodes give us a linear order with high probability, because if we assign a random number to every node with high probability, they are all different and you can order them. And that's basically how the connection goes. And that's then how we can prove this. Okay, so that's all I have to say about the main topic. I just want to mention on one slide. So all I've talked about so far is the expressiveness of graph neural networks. But of course, graph neural networks are machine learning models. We also want to talk about learnability of functions, of generalization, and so on. And I just wanted to mention a couple of recent results we have there on the VC dimension of graph neural networks. Basically, we have results for a non-uniform setting where we fix the size of the input graphs. And there the VC dimension of graph neural networks. Okay, on Boolean functions on graphs is essentially the number of actually 1 WL equivalence classes. Okay, I don't know that the 2 is a typo. Okay, and if we look at the uniform model where the size of the graphs increases, there the VC dimension is linear and the bit length of the GNNs weights. Okay, that's the results we have there, and I don't want to get into this. Let me just conclude with a few remarks. So we have this very nice flexible learning architecture, and actually we can apply it in many different settings, for example, also for solving constraint satisfaction problems. So we can also adapt them to logical formalisms. I did not talk about this. We do understand the expressiveness very well. That was the main part of my talk. Some questions remain open. If you look at the uniform version, so the main results we had in the end were non-uniform results, talking about families of graph neural networks. And what we don't understand at all is recurrent graph neural networks. Okay, so here's an example of a question there that seems kind of natural. Can we express all graph queries, compute, or all Boolean functions on graphs that are computable in polynomial time by a recurrent GNN with random initialization? Okay, that might be true. I mean, the TC0 result indicates this. I'm not sure. I really don't know, and I don't know how to attack this. Okay, and then of course there's the point. Expressiveness only tells us half the story, because in the end we want to learn these models. It should be seen, though, that most of the results we present here also have good experimental support. So if we say something can be expressed, we can usually also learn the functions. Okay, and that's pretty much all I have to say. I've just put the main references here. Okay, that's it. If you have questions, I'll be happy to try to answer them.